Today's session for the analysis and operator algebras session at the ICM. The first speaker today is Professor Mouhamed Fall. Professor Fall did his PhD at CISA in Italy and is now the endowed chair in mathematics and its applications at the African Institute for Mathematical Sciences in Senegal. And today he's going to tell us about constant non-local mean curvature surfaces and related problems.
Thank you, Paulo. So it is, of course, a great pleasure to be among the speakers of the first ICM that is organized in the Southern Hemisphere, of course. And so I would like to thank everybody who is here and all the organizers, local and non-local. So because I'm going to talk about non-local mean curvature. So the non-local people, you can think about that, or those you do not see and who their action has made this event possible. So I'm going to talk about constant non-local mean curvature surfaces. So this is a quite new subject of research, and it involves a lot of fields in mathematics, in particular partial differential equations, integral differential equations, and geometry. So to convince you a little bit about the nature of surfaces that we're going to study and their interest, then I start with some pictures that we have seen. So maybe when we do experiments, or maybe when we use mathematics. So these are, the first one is the well-known catenoid, so which you can get via soap films. And the second one is the helicoid. And then one piece of the Schreck surfaces, so Schreck surfaces are periodic ones, and then this is just one piece of them. And then you can see that all this can be made using soap films. And another one is the Costa surface. So this surface was discovered by Costa. He was a Brazilian mathematician, and he discovered this surface while he was doing his PhD. And this surface was made visible by Kaufman and Mix using computer graphics in the 1980s. So there are, of course, simple tools so to see these surfaces, so the simplest one maybe could be to use some wire, soap, water, and container. Then you make some experiment, then you see the surfaces. But there are also very interesting people who prefer, in general, to use maybe many different subjects or area in mathematics in order to grasp the geometry of these layers. So these layers, they have something very interesting. So the difference pressure between the layers is vanishing. And this is something very important. And this is once you use this, so in mathematical terms, that would mean so you have surfaces which have zero mean curvature, or surfaces which minimize area. So I start with area minimizing in this setting, and then I will tell you maybe that this surface minimize area. Something very interesting is that they are called it minimal surfaces. So even if you Google maybe minimal surfaces, you can immediately see many kind of surfaces with different geometry and topology. They are also a solution to the well-known Plato's problem. In a sense, when you fix a wire, then I would say, and I fix a curve, then I would like to say I find a surface that spans this curve with minimum area. And this surface, this problem will have been studied since several years and was finally solved by Douglas and Rado, and Douglas finally obtained the field medals, if I remember very well, in solving the Plato's problem. And so this is one simple solution of the Plato's problem, where you fix two wires, two circles, which are parallel. And the surface that you get is the catenoid. And so the first variation of area, so as I said, so these surfaces are minimizers of the energy functional. The energy functional is the area functional. And so I'm just trying to understand now what is the quantity that comes when I look at critical points, or the first derivative. In a sense, if I have a functional, just I want to find the first derivative equals 0 in order to understand all possible minimizers. So in a sense, the equilibrium surfaces. And so if I take an orientable surface, sigma, so which have this nice property, and then I call sigma t, so then it's a small, you shake the surface a little bit, so via a flow, which in the direction of a vector field v, And then if you compute the first variation of area, then you find this geometric quantity H sigma. And H sigma is what is called the mean curvature of the surface. So it is a function that goes from sigma to r. So it is defined on the surface, and it has some interesting properties that sometimes when you know how it is or you know its values, you may determine exactly the geometry and the topology of your surface. So this is the class, what is known as the mean curvature. And I am not, so maybe in the next slide I will tell you about its full expression. Well, it has many, but I'll choose just very few of them. So minimal surfaces are those I introduced before, which are those surfaces for which their mean curvature vanishes everywhere at each point. And those which are constant mean curvature, so are those for which maybe you have, they englobe some kind of air or maybe liquid or any kind of thing. So you look, so this is a constant minimization problem, and if you constrain to volume, of course you have something with constant mean curvature. So this is precisely the two notions of constant mean curvature surfaces, but the special ones are those which are called minimal surfaces. But my talk will be mostly about constant mean curvature surfaces, but via a new kind of energy, which is not only the area functional, the classical area functional, but kind of, I would say maybe an extension which involves long-range interaction, not just something that is happening near the thin layers that we see in these surfaces, but everything that is happening everywhere. And in a sense, it is an extension because it approximates well the area functional. So this is exactly what I call here the fractional area functional. So the fractional area functional is a kind of interaction when you have a set E. So it's a kind of interaction between what's happening to the set, what is happening inside, and what is happening outside the set. So it's a very interesting geometric quantities, but you see maybe this weight. So the weight, mod x minus y to the power n plus alpha, and then you see it here. And then this weight makes the integral to be finite, and so everything is well defined. The 1 minus alpha that you see in front, I will tell you what is it about later on, very soon. And so maybe if anyone who is interested in PDEs or who knows Sobolev spaces, then you can immediately see that, in fact, this is just the kind of fractional semi-norm of the characteristic function. Yeah? So this is precisely the energy of the set. And this type of energy, they have some interesting application in modeling long phase, in modeling a phase transitions, so with long-range interactions. And this was studied by many authors. For instance, there are Chen and Fifed, but this is just one of the prototype model of in the systems which involve long-range interaction. So you may also localize this energy in order to maybe study something that I would call here a non-local Plato's problem. So as I said before, so the Plato's problem is when you have a fixed curve and then you wanted to minimize area in such a way that to span, and then for which your boundary of your curve is precisely, the boundary of your surface is precisely the curve. And then the same problem, if you wanted to set it here, it will be not easy because you don't prescribe a curve, but you prescribe a set itself. And because the problem is non-local, you cannot just prescribe something very local, but you have to precise everything what is outside. And this problem is precisely the minimization of the localized perimeter, but the sets must be equal to a reference set that I had before, everywhere outside omega. And this is a problem that was studied recently by Caffarelli, Roch-Joffre, and Savin, who first proved the existence properties, the regularity of the minimizers up to a certain dimension, small set. And so this problem has attracted a lot of people in the recent years. So but there are several open questions that I would like to discuss later on related to this. It is quite challenging because studying these questions implies the study of many equations. So what we had before, we do not get it now, like something like ODEs, PDEs, theories, but now you deal really with integral differential equations. So there is one interesting remark also that I would like to tell you is that the convergence of this non-local energy P alpha to the classical area functional. So in other words, so this is a very good approximation of the classical perimeter functional. So the classical perimeter functional, if I would like to write it here, then I would not see the kind of Sobolev norm of the characteristic function. Of course, it doesn't exist. And I have to go into BV, in the theory of BV. And in this case, this perimeter, the non-local perimeter approximate well the classical perimeter. And these questions have been studied a long time ago by Davila, and then there are works, so in a pointwise sense by Caffarelli Valdinocci, and then in the gamma convergence by Ambrosio, De Filippis, and Martinez. So the first thing then we do if you have energy maybe is to look at equilibrium points, of course. And then this will allow us also sometimes to know the minimizers, how they look like maybe. So the first variation of the fractional area, maybe if I have a set, now maybe you can see that I start talking about set before I was talking about surface, but still it has the same properties just because it is more convenient to see the interactions of the interior and the exterior of the surface. So that's why I now talk sometimes about the non-local curvature of a set, but still I mean the non-local mean curvature of the boundary of the set. And so if you compute the first variation of area, you end up to a geometric quantities. And this is precisely the geometric quantity that appears in the title of my talk, which is H alpha theta omega. So this H alpha is nothing but the non-local mean curvature. So it is a function that is defined from the boundary of the set to R. And it has some interesting geometric properties that I would like to list a little bit. And so this is one of the interesting expressions that I would like also to mention is if you have a sigma, so a surface which is very nice and which is orientable and smooth, and then you have a normal vector field nu that is going up or following the surface, then in this case, if I can extend this normal a little around, just nearby the surface to a unit vector, if I compute the divergence, just in the classical way, then I see precisely the mean curvature. So this is precisely the expression that appears in the first variation of area. But the expression of the non-local mean curvature, I warn you first. So in this case, you don't compute any differential thing, but it is you evaluate some angle. So in a sense, you evaluate the angle between 2 points and the surface scalar with the norm. So it's like with the normal. So the different, and then you weight it with x minus y, and then you compute the expression. And this expression, of course, is finite. Well, of course, modulo some integration, but it's still okay. It's still okay. So there is an assumption that you should add in order to make this finite. But this, don't worry about this. It is not a big problem. And this is precisely the non-local mean curvature of the surface. So the 1 minus alpha, which comes to me once again, is just the number that I add in order to say that the non-local mean curvature is also an approximation of the classical mean curvature. So the non-local mean curvature appears first in the work of Caffarelli Sigonidis. So we will see this in one of the slides that are coming, and then also in the study of non-local minimal surfaces or S-minimal surfaces studied by Caffarelli, Roque-Joffre, and Sovin. So as a simplistic expression, I call it simplistic. I don't know if this is normal or not, but sometimes if I have anything, then I try to always to find a simpler way to write it down or maybe to understand it. So to do that, I consider a sign indicator function. So it's a function that takes -1 when I'm inside the set and 1 when I'm outside the set. And so it's visualized in this expression, so with the -1s, so which are, in a sense, all the particles which have the same, so the same properties are characterized by -1, and those which are inside are characterized by +1. And so this is how you can. And so the mean curvature is kind of infinitesimal kind of derivative of this function. the sign, the indicator function. So in a certain way, one can imagine that I am counting. It's a kind of counting the number of minus ones that is inside the set and the number of ones that are plus ones that are inside the set. I sum them up, then I average, and I find the mean curvature. So what would be very interesting or maybe very simple to see is that if I have a plane, it's very clear that what is inside and what is outside is exactly the same if I have a ball centered on it, and then which means the mean curvature is 0. So it's very easy to see it from the plane, but for the other surface that I presented before, they are extremely high. It's not immediate, but still they satisfy the same property because they bend enough that the plus ones and the minus ones, they match up and then cancel out. So the non-local mean curvature, then I remove the ball. If you see very well, I have no ball anymore, but I look at all possible interactions. So it's not something infinitesimal nearby the boundary of the surface, but it is a full averaging of the plus ones and the minus ones inside the set. And then I normalize with the x minus 1, and then I compute it. So this is precisely the non-local mean curvature. So, and this is just a principal value integration, right? So the PV here is precisely the limit here that I wanted to say, is the limit just to make the integration finite. But one would say whether this is finite or not, but of course it's finite if the set E is smooth enough, because there will be, in fact, enough cancellation between the plus and minus ones, which makes this always finite. But it's not always finite, of course, if the set is not smooth enough. And also, as I said before, you always have the approximation of the non-local mean curvature to the classical mean curvature. And this important properties also sometimes tells us that there are many interesting phenomena that was appearing in the classical case that we can recover in the non-local case. So just a little bit, maybe to get familiar a little bit with this geometric quantity, then I would like to say that you have some invariance under rigid transformation. So if you rotate, you translate, you still see the curvature of your surface. The way that it was will not change anyway with these motions. An interesting property is maybe the scaling property. So as usual, maybe one may imagine that if I have a family of balls or maybe spheres, then I send the radius to 0, then of course the mean curvature or the curvature of the surface would blow up because I go to a point, and then there is a big shift. It is precisely what is telling here, that if you scale, then you get larger. If you scale and the scaling parameter is becoming small, then you get larger and larger curvatures. And this is related to something that could be seen as a comparison principle. So it's a geometric quantity coming from an energy. I may sometimes expect something like a comparison principle sometimes. And this is telling you that if I have one set and one contains the other and touch it from inside at a point x, then I have more curvature. So the one that is inside has more curvature than the one that is outside. So this is precisely the comparison principle, and it is important in the sense that this allows you sometimes to define the notion of viscosity, a solution to the mean curvature problem. Okay. So there is a warning if anyone who wants to be interested in working with this question. There is a warning. So the comparison principle is not local at all. It's completely non-local. So the set must be contained in the other. Okay. In the infinitesimal case, so I mean the classical case, it's only enough to compare the two sets locally in order to get a comparison principle. But in this case, no, you must be inside and touch it from inside in order to get any comparison principle. So some examples of non-local minimal surfaces, I put the brackets non-local in parentheses just because they are also minima. And the first example that I want to show you is perhaps the simple ones, which is the plane and the helicoid. So for the plane, I think maybe it's very natural, maybe looking at the expression of the mean curvature here, that if I have 2 points on the plane, they are always perpendicular. So the vector making the difference between 2 points is always perpendicular to the normal, and then it has 0 mean curvature. So this is quite easy. And as I said before, for the classical one, this is very Yeah, very simple to see. But for the helicoid, it's not that immediate. So for the helicoid, it has a kind of global parameterization that can be used and then tested with the equation in order to see this. So it's not very immediate, but still it was done very recently. It was computed very recently by people, Cinti, Davila, and Del Pino in 2016. So the helicoid, if you remember in my first slide, so this you can make it via short films, and this is also one of the interesting surfaces that the non-local mean curvature can grasp. So the natural question that comes in this case is, well, okay, so maybe even me myself, I cannot tell you, beside this, almost I cannot tell you any other non-local minimal surface. I can't. But so there are people, and many people are working on this in order to get new examples. Of course, most of the examples that we find so far are kind of parallel to those that existed before. So some questions that comes in this is maybe one of the simplest one, and one which is very important is the catenoid or the Euler surface. And this was in the part of the work of Davila, Del Pino, and Wei, so in 2018. And they in fact found two types of family of surfaces. So the first one looks like the catenoid. This is very interesting already. And then the other one is somehow connected and disconnected, and is asymptotic to a cone of revolution. And these surfaces, they all have zero mean curvature everywhere, and they were found by bifurcation techniques. So in other words, so these surfaces, they exist provided the fractional perimeter is very close to 1. So as you can see, they are still partial results. So we have the geometry of some surface that we were looking at, but still all these are maybe by topological bifurcation arguments. This is already something, and these are precisely the only minimal surfaces that I can tell you for now. So it's a quite wide research field, in my opinion. And so there are some trivial examples of constant non-local mean curvature or mean curvature that I can show you, and these are those for which you have a constant. So you have volume constraints. In this case, I can give you the first examples are parallel lines. So it's very strange that parallel lines would have constant mean curvature, which is non-zero, but indeed they are, because it's a kind of interaction, not just an infinitesimal computation where you have lines have zero curvatures. So the circles is also very interesting to see, and then you can immediately see it from the formula here. So the normal in this 2 point there, so it's that you have an angle that you can, when you average it, then you get something that is positive. I think this. And there are also other ones in high dimension, which are parallel planes. So parallel planes, you can imagine they extend the parallel lines, then the sphere, which extend the circles, and the cylinders. Something new is starting. Okay, this is very interesting to have a cylinder that is coming in the game. And I can convince you about the parallel lines, which have non-zero mean curvature. And this is so the objective of my next slide, that of course, the only thing that I should look at is the projection of the y variable in this normal, so which is non-zero. And then anytime I get this, then I can start just integrating, so along the line 1, and then in this case, then I just get something in which I make change of variable and to see a positive constant, so which is non-zero. And then I keep the 1 minus alpha inside, because if this quantity 1 minus alpha goes to 0, I should get 0, of course, because this is the classical mean curvature of parallel lines. So in other words, so we still have interaction between points and other surfaces and so on. So this is something that we have to keep in mind when we work with these non-local geometric problems. Okay, so there are interesting questions that come sometimes when you study these geometric problems, is that, okay, if I have certain surfaces, so for which I know the mean curvature or the non-local mean curvature, and I have enough symmetry in the ambient space, which is perhaps the Euclidean space, then what can I say about my surface? And this is a question that sometimes I call rigidity. Rigidity is like when you know what they are precisely. And this is the first answer in this direction, so which was the characterization of the sphere. So for embedded surfaces, so this was a example to a conjecture of Hopf. So this is due to Alexandrov, and he showed that in fact the unit sphere is the only bounded connected surface with constant curvature. So this constant mean curvature, and this is somehow very interesting because I have a constant mean curvature, and then I have enough symmetry in the ambient space. And if I use this in a certain way, I would say what is precisely this surface. But this is telling just that the bubbles are round. So this is exactly the solution of the fact that if I blow up bubble, I cannot see any other shape than a round sphere. Yeah. This is exactly the rigidity theorem. And so the question that we were interested in the last years with some colleagues is the characterization of the sphere, so whenever you have, in terms of the non-local mean curvature. And this was somehow solved by 8 people, 4 in each papers, of course, and which was published in 2015. And these colleagues are Cabre and Solá Morales from Spain, Tobias Wade from Frankfurt in Germany. And this group of colleagues here, and we published, in fact, the paper in the same time. And then this is saying that the sphere is the only bounded, but not necessarily connected, non-zero, constant non-local mean curvature hypersurface. So the connectedness disappears here just because, as I was telling you, no component is left behind during the interaction. So the non-local mean curvature is an interaction which takes into account everyone. So there is everything will become into one sphere, not just different spheres or maybe many different spheres in the disconnected space with same size. And the idea of the proof here is, which I am the only proof that I am going to present in this presentation, is what is known as the Alexandrov's moving plane argument. So the Alexandrov moving plane argument is a very interesting, I would say, machinery that allows, in a certain way, to prove symmetries, whether it is in geometry problems or in partial differential equations. And I can explain you maybe in very few slides that the Alexandrov moving plane. So you have a hypersurface, I call it E, and then you fix one plane, which is the plane x1 equal lambda. You reflect your hypersurface with respect to this hyperplane, and then you start shifting the reflected surface to the first one. And then you move the process, then you start, when you move the sets E lambda, then you can move until you get something that we call interior touching, the X here, which touch here, yeah? And then, so the X here, you have, this is what we call the interior touching. The second step that would happen also, and which gives something interesting, is what we call non-transversal intersection, I'm sorry, and which is the case in which here you see that the two normals have the same normals. And then in each of these critical level, I would say critical level because these are the only interesting parts that you should take into account. If these things does not happen, then you may use some kind of arguments that allows you to continue a little bit. Okay. But anytime these things happen, then you can show in a certain way that this is, the two sets are the same. And then because you have like E and E lambda would have the same mean curvature, then if you compare and then you use just somehow this quantity that is inside the integrand, then you can see that the two sets are the same. So me, I am equal to my reflection, so I have some kind of symmetry. In the same way, also exactly, if you in the non-transversal interaction, this is the most tricky part, of course, in the proof of the moving plane argument, where you can see that E will be equal to E lambda. So if I am symmetric with respect to this, and then I can choose any direction, then I will become a sphere. So that's exactly the idea of the proof. So I have to go maybe into another game, that is the classification of graphs with constant non-local mean curvature. So anyone who is interested in working in PDEs would like to know, okay, so what is the expression of this curvature when I have a graph? And then I start with the classical one, which is quite well known, so the mean curvature, so is precisely this divergence of the gradient of 1 over 1 plus u squared. So this is a very classical expression. And this is a quasi-linear elliptic operator. So this is something very important in general if you want to study regularity and so on. So for the non-local mean curvature, the expression is very strange, right? So you have these integral equations with a q here, which measure ux minus o. So with the q, which somehow related to this, which looks like somehow the Lipschitz seminorm of u, and then you have some ux minus uy. So this is very classical to integral equations and approximate a little bit to the differential operators I would call, say, the fractional Laplacian. And this is something that is quasi-linear non-local operator, which you have to study sometimes if you want to understand the regularity of certain of the solutions to the prescribed mean curvature problems, say. And one interesting remark here that I would like to say, maybe if you notice, so if the Lipschitz seminorm is very small, then my local mean curvature or local or non-local, they are almost like the power of the Laplacian. So it's alpha equal 1 is the classical Laplacian. And this is very important in order to say, to see that somehow Lipschitz minimal surfaces are kind of smooth. And this is a kind of regularity question. And the regularity question is sometimes very linked with what is known as the Liouville theorem. So the Liouville theorem says, okay, if I have a holomorphic function which is bounded, it must be a constant. And this is very related to regularity in a sense that if you have an harmonic function which satisfies certain growth, it must be an affine function. This type of rigidity results are very connected with the regularity of elliptic partial differential equation. And this question turns out to be very difficult to study in the case of the minimal graphs, where one is interested in looking at minimal graphs which are not planes. So if you know that minimal graphs or are planes, this is a rigidity question, but this is a quite challenging problems both in the local and non-local. But in the classical case, this was studied, and then the answer is no if n is smaller than 7. So this was studied by Bernstein, DeGeorge, Almegren, and Simons. But the answer is yes if n is weight. So there are cones which are minimal graphs, and this stops the regularity for perimeter minimizing sets. So in a sense, if I have a perimeter minimizing set, it is smooth up to dimension n equal smaller than up to n equal 7. But in the non-local case, there are only one result in which we can rely on. So in dimension 2, this was studied by Figali and Valdinoci. There is no, in a sense, you have no singularities and everything is smooth in the non-local minimal surface problem. And the question remains very open and quite challenging open problems that we would like to study somehow in the near future. In fact, there are no example of non-local minimal cones that are known to be globally minimizing. So I turn now to the other rigidity result. So this is the rigidity result that comes in the class of rotational symmetric surfaces. So the class of rotational symmetric surfaces with constant mean curvature was classified by Delaunay. So these are obtained by roulette of the conics. And so they are cylinders, unduloids, spheres, and nodoids. So there is only one that is more interesting to me in this talk, which are the undulates, and I can tell you how maybe you can get it by the roulette of the conics of an ellipse, and then if you rotate, if you make the roulette thing, I don't know how to say, then you trace the focus. And then you rotate it, then this gives you the undulate. So this is the surface that is more interesting to me in this talk. Of course, this is a very good classification because it classifies all them by roulette of the conics, but also you can use ODE techniques to get the surfaces. This is something that, of course, I show you the expression of non-local mean curvature. This is something that, of course, you cannot do. And so in the non-local case, so I would say then curves and surfaces, so with constant mean curvature, they do exist and which are non-trivial, and they have the shape, so it's of a rotational symmetric surface. And if you start with parallel lines, then you can perturb them a little bit in order to get this type of lines which interact and form a surface with positive constant mean curvature. So, and this was, this comes from the work with Cabre, Morales, and Tobias Vett, so in 2016. And so the second surface that comes was bifurcation from cylinders, and this is precisely the undulates that I was telling before, and then this also has a constant mean curvature. And the last one was found somehow by my PhD students, and this comes also from, which are doubly periodic, and comes from perturbation of two parallel lines. And so these are maybe one of the few constant mean curvature surfaces that we know, but it remains still another one that I also would like to share with you. So this is, okay, so to introduce that, I will start with the global bifurcation technique. So the Delaunay surfaces, if you look at them also very well, then you can see that the cylinders somehow they shift from undulates and then they deform in order to become a spring of pearl. And this is exactly schematized here, and so you have a kind of global bifurcation, so from cylinder, undulates to string of pearl. And if you look at this question, maybe in the non-local case, this is an open problem, of course, to understand the global behavior, but we were interested more in looking at first what will happen at the limiting problem. At the limiting, we can see what is going on, and in this case, you may see that you may bifurcate, so from cylinder to string of pearls, but the string of pearls are more ellipsoid, so they are really not round spheres. This is due to some certain non-local interaction. And then I will detail a little bit more in this phenomenon. So the idea, what we did here is maybe to consider a periodic array of string of spheres, say, so which are centered at the discrete of at z, so at the discrete number, so at the at the discrete points, so in z. They are separated by R, okay, and we were trying to understand whether they have constant non-local mean curvature or not. They do not have constant non-local mean curvature, and if you compute no matter what R is, they do not. This is an open question, of course, to know what will happen if R is very close, but we conjectured that, in fact, it will not have constant mean curvature if R is close. But still, we can modify them a little bit in order to make them CMC surfaces, provided R is large. So in this case, so it is an implicit function theorem that allows you somehow to get these surfaces. And they are precisely deformation of the one that we see before. Yeah, so in this case, they are ellipsoid and they interact, so they bend more where maybe you have these non-local interactions which comes very close when they are very in the place where they are close. In fact, this is just a particular case of the result because we have, this can be proved in when you have any lattice instead of this, the Z lattice. Yeah. Okay, so there is one interesting point, so which is also a kind of so which is I'd say a motivation of on the non-local mean curvature itself. So this is mean curvature flow. So this is you try to approximate the mean curvature flow by certain diffusion problems. Okay. So if I consider a smooth set, and then I consider a stable process xt alpha. Okay, so if in this case it is alpha stable, of course, if alpha is 2, then I go back to a Brownian motion. Then in this case, I look at the solution to the heat equations, and which start at the time t equals 0 with my indicator sign, the function. Then these are the paths of the stable, alpha stable process. But then in this case, then for small time, in a certain, you see maybe that you approximate non-local, the mean curvature motion of the surface. So the mean curvature motion is usually the motion of the surface for which its normal velocity moves with the speed of the mean curvature itself. This is true if alpha is between 1 and 2. And then in this case, when the non-local interaction is higher, then you move in non-local mean curvature motion. So this is something that was studied by many people in the study or in the questions in image processing by Merriman, Benz, Osher. So the idea in this case is that maybe if you wanted to understand the motion of the two fluids, then you mix them a little bit and then you let them separate. And then this was the pointwise. So in here we have a kind of pointwise convergence, and this is due to events. And then for alpha equals smaller than 1, so this appears first in the work of Caffarelli and Suganidis, and this is precisely the first time where the non-local mean curvature appears in the mathematics literature, as far as I know. So then I have to tell a little bit about some few remarks and open problems that comes here. So as I said, the first open problems was the classifications of non-local minimal cones. This is a question that allows to understand in a certain way the regularity of non-local minimal surfaces. So what we have noticed in a certain way is that maybe this work has maybe possibly some interesting applications, because this family of non-local mean curvature surfaces, somehow they approximate in a certain way the phase diagram in block copolymer problems, in which case you see the modulated lamellae. So these are precisely kind of shapes that my students, they found. And then we see the spheres. So as I said in my previous slides, so the spheres are really, we prove them that they exist in any dimension lattice. And the cylinders, sometimes you get them from the sphere by just elongating a little bit. And so the natural question that one would ask maybe is, what about the gyroid? So the gyroid maybe is a triply periodic surface that comes in the phase diagram in block copolymers in between the lamellae and the cylinders. So these are and then the interesting question also is the existence of the non-local catenate, so in the full range of parameters. Maybe in my previous slides, then I talk about the catenate, but the existence was only when alpha is between 0 and 1, when alpha is very close to 1. And this is still a missing question. The catenate is very interesting, because sometimes if you want to build a general variety or a large variety of surfaces, you use it as next to glue different surfaces. Yeah. So there is also maybe this different open questions. This is one of them is the Costa surface, and I like the Costa surface. I would not say because I'm here in Brazil, but still it's a very interesting surface with genus. That would be the first example in the non-local theory for surfaces with genus. So I think I have only 2 minutes left, and I will just mention the existence also of periodic non-local minimal surfaces, which are the Schwarz minimal surfaces and Schreck surfaces. These are very interesting surfaces, and why I insist on this surface, because they have global parameterization. The non-local mean curvature, if you see, so you cannot left, if you change a little bit one part of the surface, you change everything. So in a certain way, it is invariant under global reparameterization, but not just by local reparameterization. So that's why one would be interested in a certain way to look at first surfaces with global parameterization in order to check by hand, which would be difficult, or maybe a little bit to add some little bit of perturbations in order to see surfaces which have this type of geometry. So I think, Pablo, I don't have time left right now. I have 1 minute, and I would like to stop here. Yes.
So thank you for the interesting talk. Are there any questions or comments? Okay. If there are no questions, then let's thank the speaker again.